Hey everybody, so today we have an interesting little lab. I'm going to demonstrate how to use some equipment today that we can use to actually calculate the speed of sound, or at least experimentally determine the speed of sound. And we're going to do this using pitchforks, basically is what we're going to do. And so we have some kind of interesting equipment to use today. So the foundational knowledge that you have for this lab is based on the concept of resonance, right? That the wavelength or the frequency of a pitchfork or a wave is going to determine the wavelength that will be able to resonate in a particular length string or something along those lines. So we've got over here a series of tubes that we will use, and this is I'll explain this in a second. And then we've got some known frequencies. So for example, I've got the pitchfork that is the pitch of 256. Here's what it sounds like. Here is what a pitchfork with a 384 frequency sounds like. And then this last one here is the shortest one, 512. So I'm going to be using all three of these. We got all three of these guys in the lab. But for today, in terms of the demo, I'm just going to use the big one today because it's a little bit easier to use for most of this anyway. So what we need to do is we need to be able to use this thing and see if we can get it to resonate inside the tube. So the hard part is, how do I make the tube the right length? If you guys remember from dealing with resonant frequencies in pipes and all that kind of stuff, it's not just any old length will do. It's got to be a length that's directly related to the wavelength of this particular thing. So the easiest way that we can do that is to use this piece of equipment right here, which has an adjustable length feature to it, which is actually kind of sketchy, but I love how creative this is. So what we've got right here is a big PVC tube. You can see it, it's on a stand down below, and there's water inside this thing. And so you can kind of see it down on here. Right there is the water level. This little piece right here is just a clear piece of aquarium tubing that allows me to see where the water level is. So the water level is actually right there, which means that right now, this is the effective height of this particular tube because it's open up on the top, and then you've got a water layer, basically a wall down at the bottom end of this. And if I have something else that I can use to adjust this, well, one way to do it would be to just dump different amounts of water in there. That's kind of awkward. So what we're going to do instead is going to use a second piece of PVC. And if I nest this piece inside this one, I can move this one up and down. So I got like this kind of thing. So you can kind of see how the water level changes as I move this thing up and down, right? Because that's still the bottom of where that water layer is. And then we can we've got our meter stick in place, and now you can kind of see where the top of it's going to be, right? So I can move this thing up and down, and I can get a full height. So you can watch the water levels moving up and down here, and then the tube I can move up and down here. So these two things together allow me to make pretty much any length resonator that I want, or any length pipe here that I want to do. And it's really the length from here to wherever that water level is down there. And that's what I've got the meter stick for. So what I'm going to be recording in the lab is going to be those two different heights, the height of the top and then the height of the water level. So you can figure out what the actual effective length of the tube is. I don't really care how far off the bottom this is. I just care from basically the water wall on one end and then the open end on the other side. So we'll be able to kind of use these, like I said, to figure out what that resonance is. So here's how this works. I'm going to take this little guy and I'm going to whack it and get it to start vibrating it. And then I'm going to hold it over the top here. So you'll see the most part is pretty quiet. There's one height where it really resonates, and I'm kind of turning my head there to try to get the microphone to pick it up. Right about there is the maximum height. So what I would really do in the lab, if it was, me doing it one-handed, I would hold this in place and I would look really close at my meter stick and figure out exactly what this height is here. And then I would look down at the bottom and figure out exactly what the height of the water level is. And now I know how long my resonating pipe is. From here to here, that particular length tube is going to be able to be the resonant, the very first resonant length that resonates at the fundamental frequency of this thing. And again, this is the 256, the long one. And again, with this one, what's kind of cool is that, it's pretty repeatable. Kind of tell where that maximum height is. It's right in there someplace. And again, I could just measure that off of there. By the way, this one, I can get a second one. It's real quiet, but it's right about there. If you can hear that at all, but it's basically right there. I can get the second harmonic. So again, the fundamental frequency was up here someplace, and then there was actually a second harmonic on this one. The other ones I won't be able to get a second harmonic on just because of the apparatus. So that was the 256. Here is the 384, just so you can kind of see what this one looks like. Right about there, huh? That looks like about the right height. A little bit shorter, right? So different frequency gives you a different height. And again, it's the height from basically the water level here to the top part up here at this point. Again, I'll post data for this. You don't have to try to read it off the screen. And then here's the last one. This is the 512, the other C. There it is right there. Hey, and then we get that. By the way, bonus points. I don't know if you noticed this, but these two tuning forks, these two, the really long one, the first one I did, and this last one that I just did, are both C notes. They're an octave apart. So I don't know if you recognize this, but the second frequency that I got off of this one, basically the same length as I got off of the little short one. They're similar because they're the same note. So this is the fundamental. The fundamental frequency was way up here someplace, and it had a second harmonic at this height. Well, that height down there is the fundamental of one octave up. So it's kind of cool. Anyway, so there you go. The kind of data that I'll post up there for you will be those three pitchforks, and I'll actually record actual heights when I can do this with two different hands. And your job will be to do a little bit of mathematical manipulation to use that distance, right, that length of our resonating pipe to be able to calculate the speed of sound. There's also going to be some error. There always is. But then you can calculate your error because, physics people, we like air. All right, there you go, guys. Enjoy, have fun with doing the little lab, and I'll see you guys around.